All right, I want to go back and record what we talked about on the theorems today, just so you have something to go back and look at in case you didn't get it all copied down, or you have it copied down now, but you just want to listen to it again and make sure that you understand what you copied down. So we started by reviewing the intermediate value theorem. So I was just trying to save some time here in the video, and I went ahead and wrote it out. And it says that if f is continuous on the closed interval from a to b, and k is any number between f of a and f of b, then there exists at least one number c in the closed interval from a to b, such that f of c equals k. So just remember, a and b are x values. That's an interval of x values. So c is an x value. F of a and f of b are y values. So k is a y value. And in terms of a picture, what that is saying is that as long as your function is continuous, all right, and you have some k value between f of a and f of b, okay, f of b could actually be smaller and f of a could be bigger. It doesn't matter as long as it's between the two. Then there has to be an x value, okay, we call that c, that corresponds to that y value on the graph, okay? And so that's all that's saying. And then in a few minutes, we will review how to apply that, how that might come up on an AP type problem, okay? All right. Okay. So once we finished reviewing the intermediate value theorem, then we moved on to the mean value theorem. And again, I paused the video while I was writing it up to make the video go faster. Plus, I hope you already have this written down in your notes. If not, you'll want to pause it and write this stuff down. All right, so the mean value theorem, it says if f of x is continuous on the closed interval from a to b and differentiable on the open interval from a to b, then there is at least one number c in that open interval such that the derivative at c is equal to the difference quotient, all right, of f of b minus f of a over b minus a. And so before we talk about what those things, like what this theorem is really saying, I wanted to go over the picture of it one more time. All right, and so what we're saying, like if I were to find the difference quotient f of b minus f of a all over b minus a, what I'm essentially doing is I am finding the slope, okay, right? The difference quotient is just another way to find the slope between 2 points. And so in this case, it would be the slope between the two endpoints. And I wonder if it's going to let me, okay? And that's close enough, okay? And so when you connect those 2 points, that's actually a secant line, okay? That's a secant line. So this part of the theorem represents the slope of a, or the secant line, okay, over that interval, okay? Now, if you remember, the whole idea of a derivative, right, is the slope of a tangent line, okay? So this side represents the slope of a tangent line at a specific point, okay? So what this theorem is saying is that as long as the function is continuous and it's differentiable, which means it doesn't have any, so it's continuous first, but then it also doesn't have any sharp corners, doesn't have any cusps, and it doesn't have any vertical tangent lines, then the slope of a tangent line at some point will be equal to the slope of the secant line between the endpoints, okay? So what would that look like on a picture? Well, in order for two slopes to be equal, all right, two slopes of lines to be equal, the lines would have to be parallel, okay? So I want to know, can I draw, all right, another line that is in fact parallel to this one, okay? So I'm just going to draw one. Let me see if, well, let me do a solid one. Of course it's, all right, I want it purple though. So then we'll click on this. Nope. Why are you, all right, maybe click on that first and then this. There we go. Okay, so let's try to make those as parallel as possible. And then I want to know, could I put that parallel line, is it going to let me drag it? Oh, there we go. Could I put that line anywhere to where it's touching the graph in exactly one spot? Okay, and I can. All right, I know it's not perfect, but let's pretend it's touching that one spot right there. Okay, now I could actually pick it up and drag it over here and touch another spot. So depending on the curve, I could have more than one place where the slope of the tangent line would be equal to the slope of the secant line, okay? Well, when we talk about that in context of a problem, the slope of the secant line is the same thing as the average rate of change. And a lot of times, I don't know what I was getting ready to write right there. A lot of times we use that average to approximate the derivative. Okay, but remember we usually do it where the 2 points are really close together, because what we're actually approximating is the instantaneous rate of change. So what this theorem is saying is that as long as your function is continuous and differentiable, there's at least one place where the instantaneous rate of change is equal to the average rate of change. Okay? So then we looked at some AP type questions. So what I'm going to do is I'm going to pause the video again. Again, you really won't see that on your end, other than when I unpause it, you're going to see the questions that we looked at in class. Okay, so we looked at some AP type questions, and I just basically gave you one stem that you're going to use for all of these questions. It says, let G be a differentiable function with selected values given in the table. Okay, so I have this table over here. I have some 4x values and then the 4y values that go with it. And my first question is there some number C in the open interval from -5 to -3 where G of C equals 3? And then, but you have to be able to justify it. So first thing you have to understand is that this, right, this is a y value, okay? So it's asking me, is there somewhere between -5 and -3 where the y value would have to equal 3? And it looks like there is, based on the table. But your justification has to prove to me, how do you know that? Okay? And the proof is going to be a theorem. All right? Now, because this doesn't say anything about a derivative, you should be thinking intermediate value theorem. All right? And so it says, like, how do we know that the intermediate value theorem applies? Okay? And so if you go back, we said that if the function is continuous and k is between f of a and f of b, all right, then there will be a place, a c value, where f of c equals that k value. So I have to somehow prove that this function is continuous first. Well, think about what the stem told you. It told you that g is differentiable, okay? So, and I might leave a little bit of space to say yes or no for the is there some number, all right? But because, all right, g is differentiable, it is automatically continuous. So it is also continuous, right? The only way to be differentiable is to be continuous first. But you have to basically tell the person reading that you know that, okay? So because g is differentiable, it is also continuous. All right, now, because it's continuous, then we can talk about the fact that we know that 3 is between 10 and -2, so IVT applies. So then the answer is officially yes. All right, and because, so then we can go back and restate. Because g is differentiable, it is also continuous. By IVT, all right, and that is an abbreviation that is allowed on the AP exam. By IVT, g of c would have to equal 3 in that interval because, all right, and this is where you have to show that the k value they gave you is between an f of a and an f of b value. Now, you don't want to actually use the y values. You want to show that you know that it's between g of something and g of something else. All right, but g of -5 is actually the +10, so that goes on the right, and then g of -3 is the -2, that goes on the left. All right, now, you could always, clarify yourself so you know that right there, but you need to refer to it as g, not just y values, okay? So yes, because g is differentiable, it's also continuous. All right, so by IVT, we know that g of c equals 3 in that interval because 3 falls between g of -3 and g of -5. All right, and that is probably the shortest way to write that answer, okay? All right, so then we took it a step further and we said, okay, well, is there some number c in the closed interval such that g prime of c equals -6? And we have to be able to justify. Okay, well, g prime is a derivative, okay? Derivative goes with MVT, the mean value theorem, okay? And so I want to know, is there a place in this interval where the derivative is officially equal to -6? But remember, MVT, the mean value theorem, guarantees that there's a place, all right, as long as the function is continuous and differentiable. Then we also have to prove that using our given information, we can actually show that the average rate of change is -6, so the instantaneous rate of change must also equal -6. All right, so again, we might leave some space for the yes and then, or no, and go ahead and start some of our justification. All right, so because, and again, you have to pretend this is not related to the last problem, so you have to restate because g is differentiable, it is also continuous. All right, and you could go ahead and say, so MVT applies if you wanted to, but like that's the most important part right now. And then you need to show at some point that you get a difference quotient that is in fact equal to -6, all right? And so it's got to be on this closed interval, so the best thing to do is start with the endpoints, all right? And so I would look at g of -3 minus g of -5 all over -3 minus -5, and I would see what I get, okay? And so then I would use the values from my table. So I would use, let's see, -2 minus 10 on top. And on the bottom, that's going to make -3 plus 5. And so I can reduce this thing, and I do in fact get -6. So this means that my average rate of change, my difference quotient equals -6. So because g is differentiable, it's also continuous. And because we have this difference quotient equal to -6, okay, MVT guarantees, let's say it a little bit different. I will kind of do it like we did the last by MVT. How do I want to say this? I'm getting myself confused. Because g is differentiable, is also continuous. And we get a difference quotient equal to -6. So by MVT, g prime of c must also equal -6. I'm just getting sloppy there. At least once in that interval. Okay? So let me go over it again. Because g is differentiable, it's also continuous. And we found an average rate of change that was equal to -6. We found the slope of a secant line on that interval that was -6. So by MVT, there has to be a place where the derivative equals -6 at least once. Okay? All right, and then part C here was asking you to justify, so we're not asking yes or no. Oh, I guess I better go do it. So we better go back and say yes, all right, because of all that stuff. All right, now I want you to justify that the graph of G has at least one horizontal tangent line, all right, on the interval from -5 to 0. Okay, well, horizontal tangent, all right, now you can include this as part of your explanation, but at some point you need to understand that a horizontal tangent line, all right, means that the slope is equal to 0. So that means f prime of c is equal to 0. So even though they didn't come out and say, is there a place where f prime of c equals 0, okay, you have to know that that's what they're asking for. All right, now I did f prime of c just to be generic, but in this case we're talking about g. All right, so then I want to go back and look at my table, and since I'm talking about a derivative equals 0, I need to see if I can set up a difference quotient and get a 0 for the difference quotient. All right, and so the easiest way to do that is, because it said anywhere over the entire interval from -5 to 0, I need to look and see if I have any y values that would subtract to be 0, because a slope is 0 if the top of the difference quotient is 0. All right, so because I do have a place, all right, I am definitely going to be able to justify this. But again, you have to treat it as if it's its own function. All right, so you have to restate that because G is differentiable, we know that it's continuous, and I'm going going to write it a little bit different than I did last time. I'm just going to say, so MVT applies. All right, and I need to prove, all right, that I do have a difference quotient. All right, we already picked the -2's, but I have to show what it's from. All right, it comes from g of 0 minus g of -3. That's how I get the -2 minus -2 on top, which means I need to use 0 and -3 on the bottom. All right, and so my difference quotient equals 0, which means g prime of c equals 0. And since we've already referred to MVT, all you have to say is, so there must be at least one horizontal tangent line on this interval. Okay, now I would definitely include this little reference here, all right, just so that you've included all the parts of the mean value theorem. Okay, I didn't say this in class, but keep in mind that a horizontal tangent, all right, if there's a horizontal tangent and the derivative is 0, that means there's a max or min on the original graph. So I thought that was kind of interesting. Okay, all right, so that's it on theorems. Hope this helps if you go back and listen to it.